As x approaches 1 from either side, from 2 plus 4x divided by 3 equals 2. First of all, is this true? I need to make sure that the author didn't make a mistake. Is this correct?
Yes.
Yes, because it's a rational function. 1 is in the domain. It's not a rational. It's actually linear. As x approaches 1 from either side, the numerator is a polynomial. I can apply the limit law, limit of the top. The limit from the top will be 6. The limit from the bottom is 3. 6 divided by 3 is 2. So this is correct. Agreed? So now I have to show, using the epsilon delta definition, that this is true. So let's do that. The double equivalency symbol. It's up to you if you want to write the entire definition in plain English, that's fine. I will not. For every epsilon greater than 0, I will find a delta positive. Nothing, they're just two symbols. Such that 0 less than, and now I would like you to fill in the gap. Or the gaps for me. I'm ready. 0 less than the absolute value of what?
A minus.
No, we cannot start with,
X
yes?
minus 1.
X minus 1, awesome. Less than,
Delta.
awesome. This will always imply
You want X of X or the actual equation?
I have to use the function now.
So 2 plus 4.
The absolute value of 2 plus 4x divided by 3,
Minus 2.
awesome. Less than,
That's
that's it. That's the entire definition. But now I have to prove this.
So can I ask a question? Do you
Sure.
get X minus 1 because the limit is 1?
No, the limit is not 1. X has nothing.
Because the limit approaches
X
1.
is, no, X approaches 1. The limit does not approach 1.
Okay, so
When we talk
X
about
approaches
X, we have to talk about 1 or A. When we talk about the function, we have to talk about the limit. So the function goes with the limit and X goes with the value of X.
So the reason why it's absolute value of X minus 1 is because
It's from here.
approaching 1.
It's from here.
Approach 1 from
So
A is
the
1.
limit of f of x as x approaches a, this is the a, and this is the L. Is that clear now?
Yeah.
Yes?
Yeah.
Perfect. So here's how we prove this. We start from the end. So this is step 1. We start with the absolute value of 2 plus 4x divided by 3 minus 2 less than epsilon. And we look at this and we look at this, and what will you do? If you know nothing about calculus, what will you do? Say it again.
so. I find the domain.
I have two fractions to subtract. There is, if I know nothing, I will still subtract those two fractions. Of course, right? There is nothing else. So the least common denominator is 3. Good. There's nothing else so far. Good. Next. Yes. Good. Perfect. Now the next step. What do you think? Good. So please tell me what to write. Very good. Good. Common sense tells us to do what next? What do you think? What is the only thing I can do now? No. I cannot inside of an absolute value ever. Not yet. I have to go through. Of course. What will I factor? Very good. Remember what my target is. That's my target. Okay. So the absolute value over 3. Now I have to remind you of the fact that the absolute value of A times B divided by C is the same with the absolute value of A times the absolute value of B over the absolute value of C. This is a property of the absolute value. So I have to write it. The absolute value of 4, the absolute value of x minus 1, the absolute value of 3 less than epsilon. But the absolute value of 4 is the absolute value of x minus 1, and the absolute value of 3 is. Remember what my target is. I want the distance between x and 1 to be alone on one side, and I want a number on the other. What should I do now to both sides to get x minus 1 in absolute? 3 over 4. So, when you give me epsilon equals 0.1, what will I give you as delta? Times 0.1 over or 3/4 times 0.1. If I say for epsilon 0.001 times 3 over 4. So that's our delta. Why? Because the limit exists. In step 2, and I don't want you to do anything, but you have to understand that in such a proof, I have to show both ways. All I want you to write is step 2 is show that delta equals 3 epsilon over 4 exists. And this is the only sentence I want you to write by reversing the steps from above. That's it.
From above.
Yes. From here, 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 here.
So literally the same thing, reverse order.
I'm sorry?
So literally the same thing, just in reverse order.
Exactly. In the reverse order. Exactly. But I don't want you to do it. I'm fine if you just remember that when you have a double equivalency, you have to show both ways. And you put this in writing and I'm fine. Yes,
So literally just put the sentence.
that's it. Show that delta equals 3 over epsilon over 4 exists by reversing the steps from above. That's it. And I like to look, yes?
Can you go over again how we made the jump to delta 3 epsilon?
Yes. By comparing this to this.
I see. Okay.
So I started from the end with the hope that I can come up with this. And I did, which means that's my delta. Yes, please.
Whenever you want us to display the answer, you want that sentence. That's it.
That's it. Okay, so let's look at one more problem, and let's say 18. And that's all I'm asking you to do. Please look at the other examples. And let's continue with continuity. So let's look at limit 3x plus 5. And this time I would like you to contribute. I'm sure you understood all the procedure, and it's not a big deal. So I have to write a double equivalency. And there are 3 symbols. If you want to remember them, fine. If you want to put everything in plain English, it's fine too. It's up to you. So
Upside down A.
for every epsilon greater than 0, yes. For every, for each, for any,
There exists.
yes, there exists a delta positive. So for each epsilon, I will find the specific delta. Each delta depends on the epsilon I create, okay? Such that,
0 plus
yes, every time I pick x close to, hey, awesome.
less than delta.
Very good, which means I cannot pick x equals -2, and I cannot be far away from -2, not further away than delta. Good. Then what will this imply for sure?
The absolute value
Of,
3x plus 5
yes,
minus or plus 1
very good.
is less than f.
Right. So every time I pick x close enough to -2, delta close, its corresponding f of x will fall within epsilon away from -1. That's it. That's it. Now what do I do? How do I start? What is this?
Value 3x.
Plus 6 less than epsilon. What could I possibly do here? And what am I after? From very beginning, I should know what I'm after.
Absolute value.
That's what I'm after, and that's when I stop.
Exactly.
Good. I'm factor out a 3, and I get x plus 2. I have to show the property of the absolute value. I cannot jump and divide by 3. I have to show the absolute value of 3 times the absolute value of x plus 2 less than epsilon. I have to show that. then I have to show that the absolute value of 3 is, yes, so now x plus 2 is less than epsilon over 3. Then delta must be, because I'm done. I found what I wanted. And this was step 1. And what do I write for step 2? Delta equals epsilon over 3 works by reversing the steps from above. Done. So initially it looked kind of weird and sophisticated, but there is nothing to it. Well, I have to be honest. And I will be honest and tell you that if the function is not linear, of course the process is more difficult. If the function is quadratic or some other type of function, cubic, who knows, the process is more difficult. I'm only interested in you remembering the process for a linear function. If you encounter another function in your homework, bring it to class and we'll work on it together. But that's all I'm really interested in. Was it too difficult? No. Is it clear why this mechanism works and it does not work for the other one? Because it's the for any or every epsilon. Okay, very good. So the next step is 2.5, which is continuity. The most important topic here is continuity at the point. Continuity at a point. So here is a function. And this is a point. I'm going to say 2, 3. And before we write the definition, what do you think has to happen at the point for a function to be considered continuous? So here is a polynomial function. I graph a polynomial function. Notice that I did not raise the pencil of my imaginary board, right? So that's a continuous function. So what has to happen at point 2, 3 for this function to be continuous there?
Has to be there.
First of all, it has to be defined. And what else?
Has to connect.
The limit from either side must equal
Right.
the function value at that point. So 3 things have to happen, right? So limit as x approaches 2 from the left of f of x must equal limit of f of x as x approaches 2 from the right, and must equal mandatory. Exactly. So continuity at the point means both sides, both limits, left and right, have to exist, have to be the same number, and they have to equal the function value at that point. Then this function is considered continuous at that point. What will you say about continuity on an open interval? When is a function continuous on an open interval? If it is continuous at every point in that interval. So when is a function continuous at a point? When both sides, both limits are the same, exist, and they equal the function value at that point. Where is a function continuous on an interval? If it is continuous at every point on that interval. That's how I know. Is this function continuous, let's say, between -1 and 10?
Yes.
Because it's continuous at every point on that interval. Okay? Can a function be continuous from the right and not continuous from the left? Before you say anything, let me show you a graph. So this is my 2, and this is, let's say, my 3. Limit of f of x as x approaches 2 from the right equals f of 2. Is this function continuous from the right? Yes. As long as the limit of the function as x approaches 2 from the right equals the function value at that point. The function is continuous from the right. Is this function continuous from the left?
Yes.
No.
No, because
That's not equal.
exactly.
Two.
What types of discontinuities? Types of discontinuities we know. 3 types. And you're going to give their names to me. Yes, this is jump discontinuity. I agree. I'm gonna present that. That's fine. You're right. I'm gonna present that in a second. Here's the second one that we just said. And here's the third one. Okay, the first one. So there are 3 types of discontinuities. What is the first type? It's called infinity. You're right. You're correct. But we like to call it infinite discontinuity. Infinite discontinuity. That's number 1. Number 2, we already said it.
Hop or jump.
Indeed, jump. Discontinuity. That's number 2. And the third one. The third one is a very important one. It's called removable. Removable. Clearly here, the limit from the left or limit from the right are not the same. The function value does not exist. Here, clearly, the function value, the function is, the limit from the left does not equal the limit from the right, so it's not continuous. But this is very special. Here, we have the limit of f of x as x approaches a from the left equal the limit of f of x as x approaches a from the right. However, it does not equal f of a. Indeed. So the removable constant, yes, please, Paul. The graph. So the removable discontinuity can be removed
Two.
because I can create a function based on this one and just define the function at that point. But there is nothing I can do here ever to change that. There is nothing I can do here ever to change that discontinuity. But this one can be removed. I can, based on this function I have, I can create another function and make it continuous, but not on the first and the second case. Okay. Any questions? Because I like to look at a few examples. Now, one, if you want to go back for a second. So these are the conditions right here, page 8. I put everything in writing for you. So types of discontinuities, infinite, removable, and jump. And I said show a graph just for yourselves. Okay, I'd like you to put those graphs here so you have idea and you remember this forever. Okay. Okay. Continuity from the right and from the left. And I said show a graph of a function that is continuous from the left, but not from the right. 10. Okay, continuity on an interval. A function is continuous on an open interval if it is continuous at every x value on that interval, correct? This is number 19. If f and g are continuous at a and c is a constant, then the following functions are always continuous. So, what does this mean? If I'm given 2 continuous functions and I add them, or subtract them, or multiply them, or divide them, or multiply one of those functions by a constant, what do I create is also a continuous function. So when I add continuous functions, subtract continuous functions, multiply by a constant. So in all these situations, see, multiply them, c times f, f over g, and of course g is not 0. So remember the concept. So every time I use continuous functions to create other functions, I create continuous functions. Of course, when I create f over g, g cannot be 0. Any polynomial is a continuous functions everywhere. So every time we encounter polynomials, we don't have any issues. They're all continuous. Any rational function is continuous on its domain, right? 1 over x is continuous everywhere except where? At 0. So a rational function is always continuous except when it's not defined. The following functions are continuous on their domains. We know that. Polynomial, rational, root. Remember we had that square root of 16 minus x squared and the domain was -4 to 4. It's continuous everywhere on -4 to 4. Trigonometric, inverse trigonometric, exponential, and log. So if you remember at the beginning of the class, I refreshed your memory on a couple of functions. So look at the exponential. Where is this function continuous?
Everywhere.
Everywhere. That's the correct answer. Everywhere. Where is this function continuous? Here I have to be careful. Greater than 0, correct. It's where it's defined. Where is this function? You already answered correctly. It's continuous everywhere except at 0, right? So these are theorems that are basically common sense. Now, this I have to explain. This is a very important theorem. It doesn't come into play right now. It will come into play a little bit later in this chapter. And this too. So these two I'll have to explain. Okay, and for now, you don't have to do anything with these two theorems. I'll explain them to you in a minute. Today, I hope, if not, next time. So you don't have to do anything with these right now. However, we already used them. So here was when we used the swapping. Some time ago, last week, we talked about the swapping of the operators. So we looked at limit of f raised to a power n when x approaches a. And we said this is the same with limit of f as x approaches a. So what did I do? I took the limit. So first, by the order of operations, I have to raise f to the nth power. But what I did was I swapped the operators. I took this operator outside and this operator inside next to f. So this is that theorem, 22 and 23, or 23 and 24, 23 and 24. So I will explain that. So this is an example. So we already used it, but we didn't talk about it yet. Okay. Then I still have the intermediate value theorem to discuss. And I think that that's the end of it after we look at examples. And that's another type of example. So this will be the end of it. But I need examples now. Slowly. On page 128, 129, I would like to look at problem 45. On 129. For what value of the constant c is the function f continuous on negative infinity to infinity? And here's the function. F of x equals c x squared plus 2x for x less than 2, and x cubed, I'm sorry. X cubed minus cx for x greater than or equal to 2. Okay, we're given a function. What type of function is this? Very good. It's a piecewise defined function. So knowing that this is a piecewise defined function, I'm trying to find this parameter. C is called a parameter. Find this parameter C such that this function will be continuous everywhere. Step number 1, I have to write that cx squared plus 2x is a continuous function since it is a, thank you, and we just stated a theorem a minute ago in which we said the following functions are continuous on their domains, polynomial. And I will say this function on, on negative infinity to 2. Step number 2, I will say that x cubed minus cx is a continuous function since it is a polynomial on 2 to infinity. Notice that I did not use the equal symbol. I could have, but that's not what I want to do. What will be number 3? That once I get that solved, I will say this function now is continuous everywhere. What do I have to study in step 3?
Function F2 has to equal y function 2.
So in short, continuity at 2. Very good. That's the key. I studied continuity to the left of 2. I studied continuity to the right of 2. But the key is what happens at 2. What has to happen at 2 is that the limit from Sx approaches 2 from the left must equal limit from Sx approaches 2 from the right and must equal perfect. If I create this condition and I determine from this condition, I determine C, I'm done. The function will be continuous everywhere. So what is the first piece?
Cx squared plus 2x.
Awesome. Cx squared plus 2x. What is the second piece?
X cubed minus c.
Awesome. So now, please tell me how much is this limit?
It should be minus
C, sorry.
4c.
4c, awesome.
Plus 4.
Awesome. So this is this limit. Perfect. What about this limit?
8 minus 2c.
8 minus 2c. Awesome. And what is this?
2.
Don't rush. How much is this?
C.
Of course. I have of c, f of 2 is still 8 minus 2c. There is no question there, right? Would you all agree? Good. So now please give me the condition that I have to solve, write and then solve, that will give us c, that will make this function continuous, guaranteed continuous everywhere. That's it. I move c, I get 6c. I move 4, I get 4. So how much is c? That's it. It's good, but there is one more tiny step. I have to put it in. I have to go back to the function and put it in. And now I will say that f of x equals 2/3 x squared plus 2x for x less than 2 and x cubed minus 2/3 x for x greater than or equal to 2 is guaranteed. Oops. Guaranteed what?
To be continuous.
Continuous everywhere. Guaranteed. We made it happen. And there is no other c value other than 2/3. This is the only one. that will make this function continuous everywhere. Any questions for me? Any questions?
On that, on questions like that, you want us to write it at the end?
Yes, you have to replace C by the value that you determined for the parameter. Yes. Yes. Any questions for me? Okay. Continuity has a very important theorem attached to it. Very important. It's called the intermediate value theorem. The intermediate value theorem. Let's suppose we are looking at a function on the interval a comma b. On the interval, closed interval a comma b. And here's our function. Here's how it looks like. This is function f of x. So the intermediate value theorem is also short for IVT. We have the abbreviation IVT. When we talk about IVT, we talk about the intermediate value theorem. Okay, so looking at the graph, would you say that f is continuous on a comma b?
Yes.
Looking at the graph, would you agree that f of a appears to be, and from the graph, is a number less than 0? Would you agree that f of b, from my graph, is a number greater than 0?
Yes.
Here's what I want to write, and you tell me yay or nay. Therefore, there exists a number c in the interval a comma b such that f of c must be, for sure, what? I did not put it on the graph yet because I'm expecting you to come up with the answer.
Between 0.
Exactly. Here is C. Exactly. But the conditions have to be fulfilled. The function must be continuous, and it must change sign on the interval, either this way or this way. Otherwise, there is no 0 in there. One more time. So the intermediate value theorem, this is one variation of the intermediate value theorem. The function must be continuous on the closed interval a comma b. It must, this says, change sign. It changes sign at least once between a and b. Otherwise, there is no 0 in there, no 0 of the function. There is no c in between a and b such that f of c is 0. So continuous, and it has to change sign, either from negative to positive or from positive to negative. And then I would say, therefore, there exists a c in the interval. This is the symbol. This one we haven't seen before. This is in. In. So this is a new symbol. We did not have this one before. And this we did have, such that. And this, there exists. So there exists at least a c in the interval a comma b, but open interval a comma b, such that f of c is 0. Why is this so important? Because in chapter 4, we will be able to solve any equation that you can think of any degree, of any type, shape, or form, with any number of the accuracy digits in accuracy that you can think of. Any equation we will be able to solve, but we will use this theorem first, the intermediate value theorem. So that's why, oops, I forgot to number my pages. So 11, 12, 13. Okay? So for example, we're not going to solve this now. Before that, notice one thing. This theorem does not solve the equation. It only tells us there is a solution here. But we have to wait till chapter 4 to find the solution. Yes, it will not tell us. So we can choose any, for example, I like to look at, let's say, 53 on 129. Yes, an example for the IVT. So e to the x equals 3 plus 2x. It's minus 2x. In this problem, they are giving us the interval. They're very generous. The interval will not be given to us. But I'm going to start with this problem. So the interval is given to us. But no, in chapter 4, it will not be given. And in the next example that I'm going to take, it's not going to be given to us, the interval. And I'll show you what to do. Okay. So we're given this equation. With algebra, no one can solve this equation. You can say, I can punch in the calculator. I agree. I can punch it in the software, in the computer. I agree. But algebraically, no one can solve this equation. And we're not trying to solve it right now. We are only trying to show that there is a solution between 0 and 1. But we don't know what this solution is. First step here is I have to move everything to one side. E to the x minus 3 plus 2x equals 0. In step 2, I have to create the function that I see. I'm just going to copy what I see. In step 3, I have to find f of and f of. What do you think?
0 and 1.
Right. And in step 2, I also have to add something about this function. Because if it does not fulfill a very important property, the IVT is not applicable. What is that very important property that the function has to fulfill?
Constant.
Exactly, it has to be continuous. So e to the x is a continuous function.
Yes.
Negative 3 is a continuous function.
Yes.
2x is a continuous function.
Yes.
I'm stating a theorem from the checklist. Any combination of continuous functions must be
Continuous.
right. That's one of the theorems. So therefore, continuous on 0, 1. Closed. And I will write for everyone to see, to remember, as a combo of continuous functions. Or if you don't like combo, you can add and subtract. Add and subtract. A combination, any combination of continuous functions is continuous. Good. So how much is f of 0? Yes, because this is 1, right? E to 0 is 1. 1 minus 3 is negative 2, and this is 0. Very good. And how much is f of 1? I only really care about the sign, not the exact number. So this will be e minus 3 plus 2. E is almost 3, right? So it's 2.7 plus 2 is 4, and 4 minus 3 is a positive number. That's all I care about. So the function is continuous on the interval 0, 1. The function changes sign on the interval 0, 1. Then what do I conclude? That by IVT, there exists a C in the open interval 0, 1 such that f of C is 0. A continuous function has to go through each and every point, so it must cross 0. It must be 0 as well. So the function must be continuous on the closed interval, must change sign. If it does, of course, if it's continuous, it must change. If it's continuous, it doesn't have to change sign, but if it doesn't change sign, then there is no solution there. It changes sign, At 0 is a negative number, at 1 is a positive number. Therefore, by the intermediate value theorem, there must be a solution there. What is the solution? I don't know yet. I have to wait till chapter 4. When we combine this theorem with Newton's method. Yes?
Why is the notation switched to FC at the end?
So there exists a C in the open interval 0, 1, such that that C makes F 0. Because it was negative at 0 and it was positive at 1, it has to pass through 0. So now I would like to look at, I still have 5 minutes, one more example, like 55, in which we are not given cosine x equals x to the third. We're not given the interval. We're not told where to look for a solution. What do we do? So first of all, I have to create the function. That's my first step, which is cosine x minus x to the third equals 0. Step number 2, this is my f of x cosine x minus x to the third. No one can solve this equation algebraically by hand. No one. There is no such thing. Okay? Then I will have to say what about this function? Extremely important. If it's not the case, then I can't say anything.
It's continuous.
Yes, it's continuous on whatever, and any interval, because both functions are continuous everywhere, whatever. And I'll figure it out in a moment, as a combination of two continuous functions everywhere. As a combo of two continuous functions everywhere. Let's put the function in the graphing calculator now. And I don't think I am ready with that. Okay, here it is. So in y equals, remember in calculus we do not use degrees. Make sure that your mode is in radian mode. So in y equals, I have cosine x, close the parenthesis, minus x cubed. Okay? And now go to second and bless you, table set. I always have to change this back to AS mode. So go to second and table. And I'm going to start with whatever you want, really. I see the software here gives me an idea of the graph. So I see there is a solution between this and this. It doesn't matter. I need to choose one very important explanation or addition to what we talked about. I have to choose a 1 unit, not more than 1 unit length interval. You cannot say there is a solution between 0 and 10. Okay? So you have to say it's between 2 and 3, or between 3 and 4, or between -2 and -1, or between 0 and 1. That is acceptable. Anything more than 1 unit interval is not. Okay, so if I write 3, I get negative. If I write 4, I still get negative. Okay, I'm going to 1. I'm going to 0. Good. So I found an interval. I don't care how many solutions does it have. But I found a 1 unit length interval, which is between 0 and 1. Perfect. So then I go to my function, and I'll say 0, 1. And I'm done, basically. Now in step 3, I have to show that f of 0 is, and I have f of 0 to be 1, and I have that f of 1 is negative 0.46 approximately. Then I'll say by IVT, there exists at least one. There exists a C in the interval open 0, 1, such that f of C must be guaranteed
0.
Any questions?